Hi, and welcome to another lab. Uh, this one is going to be about retrieval parameters. Uh, the first thing that you have to do is you have to download the two uh, files that I provided for you, magnification and phase. To do a correct retrieval, you don't just need the magnitude of the transmission reflection information, but also you need the phase information as well. So these are provided for you. These are CSD commercial software results for the split ring resonator in that unit cell that I showed you. And we are going to be using for, these files for retrieval. So let's see. Basically, all you have to do is to write down the phase and the magnification files names, and that's the D parameter. You may ask me what D is. D is the lattice constant, or the atom, the meta atom size here, that is determined to be 3 millimeters, as you can see. And by the way, let me show you how these look like. So they have S11 and frequency parameters, of course, and it goes down to here. So the rest is S21 as an example. Okay. And another good thing is to look into this file and see how it reads from another text file within the specified margins. So it doesn't read the whole thing, but just a certain region of the file. The reason is if it tries to do the otherwise, if it boldly tries to read the whole document, may not find integers. It may find strings. These kind of, for example, comments or strings, and it can't read them with this simple DLM read file. Command. I'm sorry. So you get the reflection and the transmission. S11 corresponds to reflection. S21 corresponds to transmission, and then you do the rest just like we explained in the lectures. And once you do this, uh, so it's gonna say I can't choose between the imaginary real part, so I'm just showing you the MATLAB is just showing us the imaginary component as shown here. So as you can see, for around 14 gigahertz or so, we have a negative refractive index going down to -3 even. And if I just, I did it already. Let me find the correct, this one. Yeah. So if you try to look into the whole items, epsilon, I don't know if you can see these grids clearly, but mu is negative in that region. Epsilon is also simultaneously negative, so that corresponds to a negative refractive index, basically. And that's what we retrieved as a result. So we can do something else too. Uh, let's open up was it this file? Let's see. Oh, that was the figure file. I'm sorry. Yeah. So let's try to do something else. Let's try to retrieve the data for the for our 100 cascaded layers with the meta atoms we discussed originally at the starting point of the lecture. I'm just adding the retrieval code at the end. So I'm just clicking the run button to already solve it. So let's tuck this back. Yes. So now let's try to see how let me just check. Yeah. N. Yes. So let's try to see how this will look like. So sometimes it will be out of bounds, so you may want to do this. Yeah, it's still out of bounds, but it's not critical. What I would like to show you right now is that for that 100 cascaded layers, it's not as easy as the one that we just examined for the lab. As you can see, let me go back one more time and come back eventually. So this is our negative refractive index region, but I also added the other branches here too for the cosine term to show you how the real part of the refractive index is going to be changing. And as you can see, it's just hopping to another branch here. So it's really very difficult. So for example, you have to use your imagination and creativity too. Of course, like this is the correct answer. It's coming from 0. Always start from the smaller frequency. So that's the blue one is the main branch, m equals 0, or no 2 pi addition branch. And then once you come here, the most likely result will be this blue, but it needs to go down here. And then you see that you go to the next branch. So that's the correct answer. Okay. And then this will have to be shifted down like this. And later on, blue is not the right answer. Again, you have to shift it to the next branch. So you have to add the 2 pi there. And then you have to connect it with this line here. So it needs to be continuous, but that is going to be, this is how it's going to look like once that's done. We can really see that, imagine that, but it's causing problems. And it's also causing problems here too, as you can see. So you have to really check, double check the continuity. Well, as I told you, keep these with I mean, don't literally take this retrieval very seriously. So it's just giving you an idea first, an approximation coming from the our one-dimensional transmission matrix formalism, an idea about the refractive indices of the materials that you're investigating, but that is kind of the limit. And to be honest, it's been quite a while that I've also seen a retrieval method in a paper that is most likely a decaying research area right now. And of course, the homogenization problem is a very hot subject, but the validity with respect to the Kramer-Kronix relations should be checked, double checked each time. And you can still find really nice papers, even from 2017, that's trying to find the Kramer-Kronix relationships of these refractive indices of the materials. But in the old days, people were just like publishing these kind of data by just retrieving the metamaterials, different designs, but of course that was again kind of stopped in 2010. And as I told you, that was most likely an era in which people just wanted to get a quick understanding of the refractive index phenomena to be able to come up with new designs, new metamaterials, and such. Okay, so I wanted to give you a quick background as well. So I think this is going to be the last lab we will have together. So hope to see you in another one, in another lecture, I should say.